Hello everyone, myself Yadagiri, Assistant Professor, Department of EEE, MLR Institute of Technology, Hyderabad. The last session we have discussed about the relationship between the phase and line quantities of the three-phase balanced star content network. And also we have seen about the three-phase power, three-phase balanced power going to get in case of three-phase star content network. And also what kind of relation maintained by the, what kind of relationship given by the line and phase current, that is IL equal to I phase we got. And also we have derived the line and phase voltages, that is so root 3 times of the phase voltages. So this analysis we have discussed in the last session. In this session we are going to discuss about the line and phase quantities of the relationship between the line and phase quantities of the voltage and currents of the balanced three phase delta network. So for that we need to go through the right now the overview of the session. So in this session we need to cover in case of the delta connected network, that is what do you mean by the phase voltage and what do you mean by the phase current, and also the what do you mean by the line voltage and also the line current. So what kind of relationship maintained between these two, and also how much amount of the three phase balanced power so delivered by the network as a source, and how much amount of the three phase balanced power accepted by the network as a source, as a load. So these three things we need to these many things we need to cover in this session. So now let's begin the session. So let us consider the balanced delta network. How do I say balanced? Means the each and every phase should offer the equal impedance. So based on that, we would like to say it is a balanced delta network. It's a Z ohms, and this one also we can say Z ohms, and this one also we can say Z ohm. So we need to discuss the we need to represent the first of all the voltage and the currents of the each and every phase. So for that, here the VR, VB and VYs are the three phase voltages. So this voltage is called, the voltage between the, this phase is called a VR, and this phase voltage is a VY, and this phase voltage is a VB. So because it's a R, then it is a Y, then it is a B. So what this means, it's a tapping of the R phase and also the Y phase and also the B phase. So tapping means we need to provide this tapping with the help of tapping to the load only. If it is a source, then we would like to provide the tapping to take the power from the network or power from this source. That's why we can provide the tapping. So for that, the voltage is the VR, VY, VB, and these are the phase voltages here also mentioned. Then what about the remaining thing? That is a line voltage. That is a VRY, then VBY, and also the VRB. So the voltage taken between. So the voltage taken between the, that is R to B is a VRB, and the voltage is considered between the, so that is Y to B is a VYB, and the voltage is taken between the R to B is a VRB. Voltage taken between the B to Y is a VYB. So these are the VRB, VBY, and VRYs are the line voltages. So here we want to write that same thing. That is a VRY. First we write the phase voltage VR, VY, and VBs are, phase voltages. VBs are the phase voltages. Then V phase equal to, we want to say it is a VR, VY, and VB, and this is the phase voltages. Now coming to the line voltages, this is a line 1 and line 2. The voltage is considered between the, or taken between the, this R to Y is a line to line voltage. So that we can say it is a VRY, then VBY, and also VBRs are line voltages. So these are the line voltages. So that VL equal to, we want to write VRY, VBY, and VBR. So these are the line voltages. So till now we have discussed about the, what do you mean the line and what do you mean the phase voltages. So this voltage is a, so it is a VRY. This voltage is a VRY, and this voltage is said to be, it's a VYB, and this voltage is said to be, it is a VBR. So we have already determined this all. With the help of the notations in the circuit diagram also we need to take. That's why VBR, VYB, and VRY. These are the line voltages. So here we need to observe the point carefully. That is, so whatever the phase whatever the phase voltage, so given whatever the phase voltage given by the each phase, and the same amount of phase same amount of voltage taken by the each and every line. I mean to say, so whatever the voltage given by the each phase, the same amount of phase voltage appear across the each line to line. I mean, let us say the VR is same as the VRY, and VY is same as the VYB, and also VB is same as the VBR, because there is no potential drop. That's why same amount of voltage appear across the each and every line. I mean, line to line. So that's what we can say. So in a balanced delta connected three phase network, so the line and phase voltage R should be equal. That is, line voltage and phase voltage R should be equal. So in a balanced three phase delta connected network, the line voltage R should be equal to the phase voltages. So now this is now we will consider the currents in each and every phase. Now we want to consider right now the currents in each and every phase. So for that we need to identify the current in each and every phase. So first of all, the current in the R phase. So it is act like a source pin. The current delivering from the R phase is this one. So this current is a IR, and this current is a IY. It is away from the coil or away from the phase. That's why IY. Then this current is a IB. It is. So IB. So the phase R given by some current is IR, IY, IB. And what we want to say means it is a IR, comma, IY, and IBs are the phase currents. IBs are phase currents. So what we want to write, IPH equal to it is a IR, comma, IY, and IB. So this is the phase currents of the network. Then similarly we need to find, or we need to determine we need to identify the line currents also. So for that I am going to change the color of the pointer. So then this is the current directions. So the current in the first line, this is the current line number 1 is a I1, and the current in the second line are these Y line is a I2, and this is the I3. So these are three different lines. That's why I1, comma, I2, and I3s are line currents. So these are the line currents. So we would like to say the IL equal to so this is the I1, comma, I2, and I3. So these are the line currents. So till now we have derived the relationship between the voltage and current, that is line voltage and phase voltage. We have derived the relationship, that is both are equal. I mean VL equal to V phase. And next, next we need to find the relationship between the line and phase currents. So this is the phase current, that is the line current. So let us say one phase we can consider. So this is the IR. IR is same as the I1, line current 1? No, because there will be a division taken place at this point. That's why it's not at all same as the I1. Not at all equal. The IR is the I1. So that we need to derive those relation. So in case of this network, balanced three phase delta connected network, I phase should not equal to the I line. So both are unequal. So based on that, we need to derive the relationship between the line and phase currents. For that, again we need to consider the phase sequence. So phase sequence of the system. So draw the phasor diagram of the above network, diagram of the network with the help of phase sequence, that is RYB phase sequence. Need to follow the RYB phase sequence, that is the help of the phase currents only, that is IR, IY, IB. So with the help of these currents only we need to draw the phasor diagram. So this is the IR current. So this current is a IR current. Need to maintain the equal magnitude for each and every phase. So this is the IR current. Now this is the IY current. It is. Now this one is a IB current. So these are phase sequence. We are following the RYB phase sequence. So the relation, the magnitude, the phase shift maintained by the R to B is the 120 degrees. Then this one also 120 degrees, and this one also 120 degrees. So this one also 120 degrees. So need to take any phase, any point So to get the relationship between the line and phase voltage, for that we need to apply the KCL at the node point. So apply Kirchhoff current law. Apply so KCL at any node point. We will get same thing only. So first I want to take the node number R we can consider at this point. So at this point we can consider, then apply the KCL at this point. So in at this node, the incoming currents are only the IR, the remaining currents are outgoing. I mean to say, so only incoming current is the IR to the node and the remaining two currents are outgoing. So therefore IR equal to it's a I1 plus IB. I1 plus IB. According to the phase, phase quantities. So we need to write the phase and line quantities separately. So based on that, I1 equal to, so we need to write IR minus IB. So need to take the phasor addition or phasor sum we can take based on this equation. Therefore I1 equal to IR plus of minus IB. So same we need to represent here. So the I1 value, I1 is a line current. Line current is a combination of the R and B phase current, and minus B phase current. So this is the plus B. Then we want to take the minus B. So for the minus B, we need to change the color of the pointer. So this is the plus B. Then the minus B is going to take at this position. So this is the minus B. So this is the minus IB. So this is a plus IB. Then this is the minus IB. Then we need to join these two vectors with the help of the two parallel vectors. Then we will get the resultant as I1. So this is the parallel line of IR and the parallel line of minus IB is this one. So both are going to get a common point, meet a common point. So that is, so need to take the resultant vector as, so from this point, here to here we will get the resultant as this one. So this is the I1. So I1 equal to, we want to write as IR plus minus IB based on this one. So need to assign some points here. This is a point O and this is the point A and this is the point C. From the point C we need to bisect one bisector to the OA line. So this is the bisector line on OA line. So this one assume like a point A. This is the OAB. This one we need to take C. So the angle between these two is a 90 and angle between these two is a 90 also. So both are coincident and both are equal triangles. So for this we need to find the cos value, cos 30 value. So this angle should be the 60 degrees and this angle should be the 30 degrees. So from the triangle OBC. So this case we need to consider the OBC. So from this we need to find the cos 30 value. Cos 30 equal to the adjacent upon the hypotenuse. Adjacent is it is a OC upon OB is the hypotenuse. OC upon OA. Sorry, OC upon OB. So based on this we need to find the cos 30 value. Then the cos 30 equal to the OC is the half of the OA. We can write that is half of the OA. So divided by, it is again OB only. Therefore cos 30 equal to the half of OA means it is a half of the I1. It is a half of the I1. So divided by, this is a OB means it is a IR. Half of the I1, half of the I1 is we can taken as a OA and the OB is the IR we have taken. Then need to find the cos 30 is a root 3 by 2 equal to, then here 1 by 2 times of I1 is, we can say it is a IL and then IR is as a I phase. IR is a I phase we can consider. Then both rows are going to get cancelled. Therefore root 3 equal to the, so we got like IL upon I phase. IL upon I phase. So therefore I phase equals to the IL times of root 3. So this is the relationship between the line and phase currents. So the IL equal to the, so root 3 times of I phase we got, and I phase equals to the IL by root 3 we got. So this is the relationship derived. So between the line and phase currents, and also we need to apply the same KCL at the node other, the other node means y node, we will get the same thing only, and also apply the we will get the we'll apply the KCL at the node B, also we'll get the same relation. So based on this one, we need to plot the phasor diagram like so between the RB and also the YB and also the BR, so we'll get the same relationship only. So that is the relationship between the voltage and currents in case of the delta connected network. Now we need to find the in case of the star connected network, the power. So here the delta only it is. So need to find the power, three-phase power in delta connected balanced system. So each phase, first we need to take the power in each phase. Power in each phase, that is, so P phase, P1 phase equals to the V phase, comma I phase, then cos phi phase. So in case of the three-phase power in three phase, that is the P3 phase equals to the, so 3 times of V phase, then I phase, cos pi phase, then 3. So the line and phase voltage are same in case of delta. The line and the phase currents are different. That is a root 3 times of IL. Sorry, IL upon root 3 we got here. It's a IL upon root 3 into cos pi L. So root 3 here. So root 3 gets cancelled. Then power in 3 phase equals to the, so root 3 times of VL, then IL cos pi L. So this is the power in case of the, so 3-phase balanced delta connected system. So summary of the session. So till now we have derived about the relationship between, so the line and phase currents. So in case of the delta connected network, the line currents are not equal to the phase currents. Means IL equal to the, so root 3 times of I phase we got. So based on this one, I phase equals to the IL upon root 3 we got. So this is the relationship we have derived till now. Then whatever the voltage means, so the in case of the balanced 3-phase delta connected network, line and phase voltage are same. So this is the VL equal to V phase. In case of the line currents, both are unequal. In case of the line and phase voltage are equal. In case of the voltages, both line and phase voltage are equal. Then the 3-phase power in 3-phase delta connected network is a root 3 times of VL, then IL cos phi L. VL, then cos phi L. So this is the 3-phase power in delta connected 3-phase system. Balanced delta connected 3-phase system. So this is the end of the session. So thank you and thanks for watching the session.